Now, as we have discussed about the magnetic field at any point due to a wire which is carrying the current. Right now our focus will be to find out the magnitude and the direction of B, or the magnetic field, at the center of a current carrying coil. First of all, let us draw the diagram for it. Say for example, this is a circular current carrying coil, right? And we need to find out the B at the center. So say for example, this is the center. We need to find out the B. And as we know that we need to define a very short length dl, where the total L is actually this total length of the coil. So now we are taking dl, a very small part of the coil, right? Now over here, if we extend this dl, we shall see, if say for example the current is being in this direction, so the dl direction would also be like this. This is the dl direction, right? And now this is the distance between this point, the point wherein we are said to find the magnetic field, right? And what is the distance? If this entire one is a circle and we know that this is the center, then this one will be equals to r, where small r is the radius for this circle and the length of this is dl. Now let us deduce, as we know over here, that B is equals to mu naught divided by 4 pi multiplied by I dl sine theta divided by r square, where r is the distance. Now look out, this whether will be d or dB, because this is dl. Whatever we are calculating over here for this dl will be for this small length. Another small length may be in like this, and it will, like force, it will be creating another B over in this region. So each and every dl on this coil will actually make up their individual magnetic field. So whatever we are calculating right now, it will be dB, because this is the small magnetic field we are intending to find out for this small length, right? Now over here observe, this is dl. This is so small that like it will, whatever this line is, the dl, it will act like the tangent to this circle, because this is so small, right? And if this is the tangent and if this is the radius, we know that the angle between the tangent and the radius is always equals to 90 degree, right? And what is the tangent over here? This is dl. And what is the radius? It is the r. So this was actually the theta, right? This one, and the theta over here is pi by 2. So we can find out B is equals to integration mu naught divided by 4 pi multiplied by, this will be I multiplied by dl sine of pi by 2 divided by r square. Now it would be integrated from where to where. Say for example, if we mark one point over here, this as the initial point. This is 0. And what will be the final point? We will traverse along the entire loop and again we will come down over here. So we have started from over here and we will again come down over here, right? And the total, I mean the final, will be over here as the perimeter of loop. Now this loop is in the form of a circle, right? And if this loop is in the form of a circle, then the perimeter of the loop will be equals to 2 pi multiplied by r. Or this same thing is equals to L, or the length of this loop. So we have to integrate it from 0 to 2 pi r, right? So we will get it as mu naught constant, 4 pi is constant, I will also remain constant because the I does not vary upon this length of this coil, and sine pi by 2 is equals to 1. So we can write it as mu naught divided by 4 pi. The radius will be constant over here, multiplied by the, like I will also come out because it is a constant, it won't change, from 0 to 2 pi r. Then it will be mu naught 4 pi I r. This will be r square and this will be dl. And the value of sine 90 or the sine pi by 2 is equals to 1. Right? So this will come out to be mu naught multiplied by I divided by 4 pi r square multiplied by integration of dl over from 2 pi r to 0. This will mean the 2 pi r minus 0, or simply it is 2 pi r. So observe over here that this r will cancel out 1 in the denominator, leaving out only 1 r in the denominator. This pi will get cancelled out and this 2 will cancel this 4, leaving only 2 in the denominator. So actually the B what we will get in this scenario will be equals to mu naught I divided by 2r. So the magnetic field at the center of a current carrying coil will be equals to mu naught multiplied by r divided by 2r, or 2r will mean the diameter of this coil, right? Now for example over here in this scenario there are n number of turns for a coil having n number of turns, right? How the n number of turns? Because say for example over here this is a turn, and again over that, starting from where it ended, there will be another turn like this. So there are n number of turns. Okay, so these turns will actually pile up like this. Okay, as being this is the same like a coil underneath it, and a coil underneath it likewise. So at that moment, this will be B for n number of turns will simply be equals to B for 1 multiplied by n, which will be equals to mu naught Ni divided by 2r. See, mu naught I divided by 2r, only simply multiply it by n, or the number of turns on this occasion. Yeah, that's very good that we have found out that what is the magnitude of V. What will be the direction of V? We need to find it out. For over here again, we have to apply the corkscrew rule or the Maxwell's right hand thumb rule. Now take your right hand and place the fingers, the other fingers, in such a way that it indicates the flow of the current. Over here, likewise. So now your thumb of the right hand will indicate the direction of the flow of magnetic field. Now where is it flowing? The magnetic field. It is flowing towards the reader. So we can say the symbol of this as likewise. As we know that this symbol indicates that the magnetic field now is coming towards the reader, or the magnetic field is coming out from the whiteboard or the paper. So we can write the direction for anti-clockwise I, this anti-clockwise I direction. V will be outwards from paper, or simply this symbol, right? And if we say that the direction for clockwise I, then B, the direction of this B will be inwards into paper or whiteboard or anything, and is denoted by this cross symbol, right? There is another notation, like say for example we check it likewise. The current is anti-clockwise over here, and this is as such. Over here, if we make the anti-clockwise currents as such, likewise, if we make, say for example, this one over here, this is the direction, right? The green line direction is likewise, and we are making another thing like this in the same direction. Okay, now again this is going up this direction, we are making another one inside like this. And now let us fix up a point at the center of this circle, right? Join the two tails. I repeat again, join the two tails of these arrows, of these red arrows. See, this is N. So this is the North Pole. So if ever we see that the I is anti-clockwise, it means that we are seeing the head of the North Pole. Because if it is like this, which means that the magnetic lines of force within a bar magnet is flowing from south to north, not from north to south, okay? Because the magnetic lines of force will flow only from north to south in the occasion when it is outside the bar magnet. And over here, if we are keeping this, the curling of other fingers on the right hand as the direction of the current, this thumb will actually indicate the direction of the bar magnet. So whatever this direction indicates, it indicates the direction of the bar magnet. If the North Pole is towards you, which means that now within that bar magnet, this is an imaginary, okay, this is an imaginary bar magnet. So within that bar magnet, that magnetic line of force will flow from the south pole to the north pole, and you are seeing the north pole now. In the other instance, if we do make out, say for example now, clockwise current, right? Over here, likewise, let us make that this is, say, for this, and over here it is coming down again, like this, right? Again, the same thing. Fix up a point which is the center, and as I said, that only join the tails of these lines. Simple. This is joined, this is joined. What is it looking like? It is looking like S. So if you are looking at from the paper, or you like a question, if it is given that this is the current, okay, in the clockwise direction, simply without using any corkscrew rule or without using your fingers of your right hand, you can simply say that we are now saying the head of the south pole, right? This convention is also applicable anywhere where actually we want first deductions, right? Otherwise, not a problem. If you want to pick up your fingers, or if you want to see that what the direction of your thumb is giving, that is actually the Maxwell's right hand rule, or right hand thumb rule to be precise. So this is all about the magnetic field at the center of a current carrying coil, and we do see that the direction of it is that it is coming outwards from the paper, right? Thank you.